All right, welcome to the deep dive. Today we're taking a look at something pretty fundamental, electromagnetic induction.
Yeah, it's a big one. It's how magnetism and electricity, kind of connect and work together. It's pretty amazing.
It really is. When you first hear about it, it almost feels like, I don't know, magic or something.
Oh, yeah, absolutely. And it's everywhere, really. So much of our tech, the way we get power to our homes, all sorts of gadgets we use every day, they all rely on this principle. It's about how a change in a magnetic field can actually create electric forces and currents.
Exactly. And that's precisely what we're going to try to unpack in this deep dive. We've got, let's see, a whole chapter here, jam-packed with info. It lays out the initial experiments, the laws that govern this whole thing, and even some really cool applications.
Yeah, it's a good one. Really gets into the nitty-gritty.
Right. So our mission today is, I guess you could say, to really understand, as best we can, the core concepts of electromagnetic induction, just as they're presented in this material.
Makes sense to me.
So where do we even begin?
Well, the chapter starts off by, it sort of lays out the groundwork with some really key experimental evidence. The kind of stuff that first hinted at this connection between magnetism and electricity. So picture this. You've got a coil of wire hooked up to a galvanometer.
A galvanometer, right. Okay, that's like a super sensitive instrument, right?
Exactly. It's like a needle that moves even with the tiniest bit of electrical current. So you have your coil and your galvanometer. Now imagine you bring a magnet close to that coil.
Okay, I'm picturing it. So what happens? Does the needle go crazy?
Well, that's the interesting part. The needle only moves, showing a current, while the magnet is in motion, like when you're moving it towards or away from the coil. But as soon as you stop the magnet, even if it's right inside the coil, the current stops too.
So it's not just about having the magnet and wire near each other. It's the movement, the change that's making the electricity.
Yeah, you got it. That was a huge clue early on. And they didn't stop there. They did other experiments too. Like imagine two coils placed close together, right?
Okay, two coils.
You can create a current in one of the coils, not just by moving the other coil, but also by, and this is wild, just by changing the amount of current flowing through that other coil, even if it's not moving at all.
So it's like any shift, any change in the magnetic, I guess, environment around a conductor can trigger an electric current.
Yeah, that's the big takeaway. A changing magnetic field, that's the essential ingredient for inducing what we call an electromotive force or, EMF for short. It's basically a voltage that can push a current.
Okay, so change is the magic word,
Hmm.
but how do we actually measure this magnetic stuff that's changing?
Right. That's where we need to talk about magnetic flux.
Magnetic flux.
Yeah. It's often represented by the Greek letter phi with a subscript b, like this V. And it's essentially a way to measure the total amount of magnetic field lines that are passing through a specific area.
Okay, so like if you imagine a loop of wire, magnetic flux is like counting how many of those invisible magnetic lines are going through it.
Yeah, that's a good way to think about it, to visualize it. And the chapter gives us a more, I guess you could say, formal definition. So for a uniform magnetic field, we can call it B, right? And this field is passing through a flat area, A. The magnetic flux is calculated by, it's the dot product of those two vectors, baby, in the EOA, like that.
Okay, so B is the magnetic field strength and A is the area. But what's this dot product thing tell us?
It's basically a way to figure out how much of the magnetic field is actually passing through that area, considering the angle between them. Like think of rain hitting a window.
Right.
If the rain is coming straight down, perpendicular to the window, you get the most rain hitting the glass, right?
Right.
But if the rain is hitting the window at an angle, kind of glancing off it, less of it actually makes contact.
Right, I get it.
So the dot product is like that. It helps us figure out how much of that magnetic rain is actually going through the area, taking into account the angle, we can call it, between the magnetic field and the normal to the area.
The normal, meaning perpendicular.
Yeah, exactly. So mathematically, it ends up being B times A multiplied by the cosine of that angle.
Got it. So magnetic flux, it's a way to quantify, to put a number on, how much of that magnetic field is actually interacting with a loop or an area, and we have to take into account its orientation too.
Exactly.
And as we saw from those early experiments, it's the change in this BB that really matters.
Right. A static magnetic field, even a strong one, won't induce a current if it's just sitting there. It's only when that magnetic flux through the loop changes that we see the effects of induction.
Okay, so we know that what? A changing magnetic flux induces something electrical, but how do we figure out How much is induced?
That's where Faraday's law comes in. It's like the quantitative heart of this whole thing. It tells us exactly how much electromotive force, that EMF we talked about, is induced by a changing magnetic flux. It's a pretty concise law, actually. It says that the induced EMF, we'll call it E, in any closed circuit is equal to the negative of the time rate of change of the magnetic flux through that circuit. So E equals dB dt.
Okay, so the faster the magnetic flux changes, the bigger the induced EMF.
Precisely. Big change, big EMF, the dB dt part.
Yeah.
That's just a fancy way of saying how quickly the magnetic flux is changing over time.
Okay. And what about that negative sign? Seems important.
Ah, that negative sign. That's the key to Lenz's law, which tells us about the direction of the induced current. We'll get to that in a sec. But before we do, the chapter also mentions something interesting. If you have a coil, let's say with n turns, and the magnetic flux through each turn is basically the same, then the total induced EMF is simply multiplied by the number of turns. So E equals n nab d dt, more loops, more voltage.
Makes sense. It's like each loop is adding its bit to the total electrical pressure. So Faraday's law gives us the amount, the magnitude of the induced EMF. Now, about that negative sign and Lenz's law, what's that all about?
Lenz's law, it's all about the direction of the induced current and, therefore the induced EMF as well. It's basically saying that nature doesn't like change, at least not in the electromagnetic world. It tries to resist it. So Lenz's law says that an induced current will always flow in a direction that creates its own magnetic field, and this field opposes the change in magnetic flux that created the current in the first place.
Okay, can we maybe break that down a bit? I think I'm getting lost.
Sure. Think of a loop of wire, right? And you're moving the north pole of a magnet towards it.
All right, got it. Moving the magnet closer.
As that magnet gets closer, the magnetic flux through the loop increases. More magnetic field lines are passing through it. So what does the loop do? According to Lenz's law, it's going to create its own magnetic field to push back against that increase. Basically, it tries to make its own north pole to repel the incoming magnet.
It's like the loop is saying, hey, back off.
Exactly. And it does that by having a current flow in a specific direction. That's where the right-hand rule comes in handy if you want to figure out the exact direction. And of course, if you were pulling the north pole away from the loop, the flux would decrease. In that case, the induced current would flow in the other direction, trying to attract the magnet back, resisting the decrease in flux.
So it's always fighting against the change, trying to keep things the same. And the chapter mentions a link to the conservation of energy here, right?
Yeah, energy conservation is a big deal in physics. And it makes sense here, too. Think about it. If Lenz's law were the opposite, if the induced current actually helped the change along, well, you'd have this runaway effect. A small change would create a bigger change, and then an even bigger change. It'd be like getting free energy, which we know doesn't really happen. Lenz's law, with its opposition, makes sure you have to put in work, like literally moving that magnet to create the induced current. The energy you're putting in gets converted into electrical energy.
So it's a self-regulating system. I like it. All right, so Faraday's law gives us the amount. Lenz's law gives us the direction. We're getting a pretty good handle on this induction thing. Now, there's also this thing called motional EMF. Is that something completely different, or is it more like just another flavor of Faraday's law?
Motional EMF, it's really a specific case of electromagnetic induction. It happens when a conductor moves through a magnetic field. You can totally understand it using Faraday's law, thinking about the changing magnetic flux as the conductor cuts through the field lines. But there's another way to look at it, too, from the perspective of the magnetic force that acts on the charges inside the conductor.
Okay, so let's say we've got a metal rod moving through a magnetic field. What happens to the electrons in that rod?
Well, because the rod is moving, those electrons are moving too, right? And when charges move through a magnetic field, they experience a force. There's a formula for it, QVAB, where Q is the charge, V is the velocity, and B is the magnetic field. This force makes the positive and negative charges in the rod separate. One end becomes more positive, the other more negative.
And that separation of charge, that creates an electric field within the rod, which means there's a voltage across it.
You got it. And that voltage, created by the rod moving through the magnetic field, that's what we call motional EMF. There's even a simple formula for it. If you've got a straight conductor, length L, moving with a velocity V perpendicular to a uniform magnetic field B, the motional EMF is just E equals VBL.
Nice and simple. What if things aren't perfectly perpendicular, though?
Right. In a more general case, the direction of motion and the magnetic field might be at some weird angle to the conductor. So the chapter gives a more general formula, EV, AE, BE, EL, where the integral is taken along the length of the conductor. It's a bit more mathematically involved, but it covers those more complex situations where the velocity and magnetic field might change along the way.
Okay, so motional EMF, it's using magnetic forces to create voltage from movement. The chapter gives some examples of this in action, like the slide wire generator. Can you explain how that works?
The slide wire generator, oh yeah, it's a classic. It's a really elegant way to demonstrate this whole thing. So picture this. You have a U-shaped conducting track and a conducting rod that can slide along the arms of the U. You put this whole setup in a uniform magnetic field, and you make sure the field is perpendicular to the track.
So the rod is like completing the circuit, making a loop as it slides.
Exactly. And as that rod slides, the area of the loop changes, right? Which means the magnetic flux through the loop is changing too.
Right. Bigger loop, more flux. Smaller loop, less flux.
You got it. And that change in flux, that's what induces the EMF and the current, according to Faraday's law. But you can also think of it from the motional EMF perspective. As the rod moves with some velocity, it's cutting through those magnetic field lines. So you get that separation of charge, that voltage across the rod, and that voltage can drive a current through any circuit connected to the track. So it's a really cool example of how Faraday's law and the concept of motional EMF are describing the same thing, just from different angles.
This makes sense. The chapter also talks about the Faraday disk dynamo, sometimes called a homopolar generator. That one seems a bit different. There's no loop that's changing size, right?
The Faraday disk dynamo, yeah, it's a cool one. It's mostly about motional EMF. So imagine a conducting disk and it's spinning in a magnetic field, but the field is aligned parallel to the axis of rotation.
So like if the disk is a spinning coin, the magnetic field is going straight up through the center of the coin.
You got it. Now think about a tiny piece of that disk, some distance from the center. It's moving with a velocity that's perpendicular to the magnetic field. So you get a tiny motional EMF in that little piece. And all those tiny EMFs, they're kind of connected in series along any radial path from the center to the edge of the disk. So you end up with a steady DC voltage between the center and the edge.
Interesting. So you get a usable voltage even though there's no obvious loop that's getting bigger or smaller.
Right. It's a neat demonstration of how versatile this concept of motional EMF can be.
Okay, so we've covered a lot of ground here.
Yeah.
But the chapter goes even deeper. It starts talking about induced electric fields. That sounds like we're moving beyond just voltages in wires. It's like something more fundamental is happening in the space itself.
Yeah, you're right. We usually think of electric fields as being created by static charges, like in electrostatics.
Yeah.
But Faraday's law shows us something deeper. A changing magnetic flux can create what we call a non-conservative electric field. And this can happen even in empty space where there are no charges around.
Non-conservative. What's the difference between that and the regular electric fields we're used to?
Well, in a conservative electric field, the work done to move a charge between 2 points doesn't depend on the path you take. It's always the same. And if you move a charge around in a closed loop, back to where you started, the net work done is always zero. But with an induced electric field, that's not true anymore. You can actually do net work on a charge moving in a closed loop. It's a different beast altogether.
So it's like the changing magnetic field is stirring up the electric field in space, even if there are no charges there to start it.
That's a good way to picture it. It's a very dynamic relationship. The changing magnetic field is creating the electric field.
The chapter gives some examples of this in action, like electric guitar pickups. How do those work?
Yeah, in a guitar pickup, you have a coil of wire near the strings, and usually there's a permanent magnet under the coil and the strings. When a guitarist plucks a string, it vibrates, right? And that vibration changes the magnetic flux through the coil. The moving string is messing with the local magnetic field.
Right.
So you get an induced electric field in the coil, and that pushes a current through the wire. And that tiny electrical signal, that's what gets amplified to create the sound.
So it's the string's vibration that gets turned into an electrical signal thanks to this induced electric field.
That's pretty cool.
And what about alternators in cars?
Alternators, they use the same basic principle. Inside an alternator, you have a spinning part with magnets, called the rotor, and a stationary part with coils, called the stator. As the rotor spins, the magnetic flux through those stator coils keeps changing, so you get an induced electric field and an alternating current, or AC, in the wires. And that AC electricity can then be used to power the car's electrical system.
Okay, so from a vibrating guitar string to a spinning alternator, it's all about changing magnetic flux and the electric fields it creates. Now, there's another concept the chapter introduces, eddy currents. What are those all about?
Eddy currents, they're like induced currents, but instead of flowing in a nice, neat wire, they flow in loops within a big chunk of conducting material.
So if you have a solid piece of metal and you expose it to a changing magnetic field, you get these little swirling currents inside it.
Exactly. And just like any current flowing through a material, these eddy currents create heat. This is due to the material's resistance. And this heat can be useful, but it can also be a nuisance.
Useful how? The chapter mentions induction furnaces.
Right. Induction furnaces, they use eddy currents to heat things up. Pretty clever, actually. They apply a strong alternating magnetic field to a piece of metal that creates big eddy currents in the metal. And because the metal has some resistance, those currents generate a lot of heat. It's a very efficient way to heat or even melt metal.
So instead of using an external heat source, you're using the induced currents to heat the metal directly from within. What about metal detectors? Do those use eddy currents too?
Yeah, they do. Metal detectors typically have a coil that creates an alternating magnetic field. When that field hits a metal object, it induces eddy currents in the metal. And those eddy currents create their own magnetic field. The metal detector then senses this change in the magnetic field, and that's how it knows there's metal nearby.
So the metal object creates its own little magnetic signal because of the eddy currents. Pretty clever.
Yeah.
But you mentioned that eddy currents can also be a problem, right?
Yeah, they can be a source of energy loss. The chapter talks about transformers as an example.
Transformers, those use induction to change the voltage of AC electricity, right?
Exactly. And they usually have a core made of iron to help guide the magnetic flux. But, you guessed it, that changing magnetic flux also induces eddy currents in the core itself. And those eddy currents create heat, which is wasted energy. To minimize this loss, transformer cores are often made of thin sheets of iron, separated by insulation. That breaks up the eddy currents, reducing the energy loss.
So you want the magnetic flux to flow easily, but you don't want currents flowing in the core itself. Makes sense. All right, we're getting near the end of the chapter, and it introduces something pretty big. Maxwell's equations. They're like the fundamental laws of electromagnetism, right?
Maxwell's equations, yeah, they're a big deal. There are 4 equations that together describe pretty much everything about classical electromagnetism, and they're elegant, too.
Elegant, as equations go.
As equations go, yeah. The chapter presents them in integral form, which is maybe a bit technical, but basically they relate electric and magnetic fields to each other and to charges and currents.
So they tie everything together. Can we go through them one by one just to get a basic idea of what they say?
Sure. The first one is Gauss's law for electricity. It basically says that electric charges are the sources of electric fields. The more charge you have in a region, the stronger the electric field will be.
Okay, that's kind of intuitive. What about the second one?
The second one is Gauss's law for magnetism. And it says that there are no magnetic monopoles, like isolated north or south poles. Magnetic field lines always form closed loops.
Right, they always come in pairs. What about the third equation?
That one is Faraday's law of induction. It's the one we've been talking about this whole time. Changing magnetic flux creates an electric field.
The heart of the matter. What about the last one?
That's the Ampere-Maxwell law. It describes how magnetic fields are created. The original Ampere's law said that currents create magnetic fields, but Maxwell added a term to it called the displacement current, which accounts for the fact that changing electric fields can also create magnetic fields.
Displacement current. Why did he add that?
Well, it was a really insightful addition. It solves some problems that the old Ampere's law couldn't explain, like what happens when a capacitor is charging. There's a current flowing in the wires, but no actual current between the plates, but there's a changing electric field between the plates. So Maxwell realized that this changing electric field should also contribute to the magnetic field.
So it was about making the equation work, even in situations where there's no actual flow of charge, just a changing electric field.
Exactly. And it's this addition that really completed the symmetry of Maxwell's equations. Changing magnetic fields create electric fields, and changing electric fields create magnetic fields. It's this beautiful back and forth that makes electromagnetic waves like light possible.
That's amazing. So those 4 equations really do seem to cover a lot of ground. And the chapter finishes up by touching on superconductivity. That's when materials lose all electrical resistance, right?
Superconductivity, yeah, it's a wild phenomenon. Below a certain temperature, some materials just, they stop resisting the flow of electricity altogether. Zero resistance.
So you could have a current flowing in a loop forever without any energy loss.
Theoretically, yeah. It's pretty mind-blowing. And there's some interesting magnetic effects, too, like the Meissner effect.
The Meissner effect, what's that?
It's when a superconductor expels magnetic fields from its interior, like it just pushes them out.
So no magnetic field can exist inside a superconductor.
Right. It's different from a perfect conductor, which would have zero resistance but would still allow a magnetic field to exist inside. The Meissner effect is a purely quantum mechanical effect.
Interesting. And the chapter mentions something called a critical magnetic field, too.
Yeah, the critical magnetic field. It's the maximum magnetic field strength that a superconductor can withstand before it loses its superconductivity. Above that field strength, it goes back to being a normal conductor.
So it's not like superconductors are immune to magnetic field. There's a limit.
Right. But even with those limitations, superconductors have some amazing applications. They're used in MRI machines, particle accelerators. They might even be used in levitating trains someday. They're also used in extremely sensitive magnetic field detectors.
It's incredible how these quantum effects that happen at ultra-low temperatures can have such big impacts on technology.
Well, we've covered a lot of ground in this deep dive. We've gone from the basic idea of electromagnetic induction to Faraday's and Lenz's laws, motional EMF, induced electric fields, eddy currents, Maxwell's equations, and even superconductivity. That's a lot of physics.
It's a pretty comprehensive chapter, that's for sure.
It really gives you a sense of how important this whole concept of electromagnetic induction is. It's the basis for so much of our modern technology.
Absolutely.
It really makes you wonder, though, what kind of crazy inventions we'll come up with in the future as we learn more about how to manipulate these fundamental forces. And on that note, I think we've successfully covered all the main points of this chapter on electromagnetic induction. Thanks for joining us on this deep dive.
My pleasure. It was a fun one.